Good morning, students. So we were discussing about multiple linear regression models and the problems that we can face with the multiple linear regression, and also how to overcome that. And especially we were talking about the Box-Cox transformation during the last lecture. So today we are going to discuss about DOE with ANOVA, that is design of experiment and analysis of variance. So when we were talking about the simple linear regression and the multiple linear regression, we actually came up with the ANOVA table. So by now, you know what is the ANOVA table. And if you can remember in ANOVA table, when it comes to simple linear regression or multiple linear regression, we have we calculated three values, that is the total sum of squares, regression sum of squares, and error sum of squares. And then we calculated their mean squared values and then the F value. So based on this F value, we can conclude whether the ANOVA, the regression model is significant or not. So that's what we did in simple linear regression and in multiple linear regression with the use of ANOVA table. So when it comes to design of experiment, so this design of experiment, it's a very systematic method where we deal with the factors. So when it comes to design of experiment in our process, there are different factors, and these factors are affecting our process. So we are conducting this design of experiment in order to find the cause and effect relationship. Because when it comes to ANOVA table, what we can find is the variation between groups. So whether the means are different between groups. So there we cannot come up with using ANOVA cause and effect relationship. But when it comes to design of experiment, we can talk about the cause and effect relationship. So that's what we do in DOE, design of experiment. Now, in this case, when it comes to ANOVA with design of experiment, what we do is we believe when you take now, since we have factors in design of experiment, we believe for each factor level, there is a probability distribution. Now, for an example, if you take, if we are going to study about 3 fertilizers, which are affecting for the yield of, let's say, tomatoes. So in this case, if you take fertilizer 1, fertilizer 2, and fertilizer 3, all are having the same probability distribution. So in this case, we believe that each probability distribution is normally distributed and they're having a constant variance, and the variance is same. And also, if you take the observations for particular factor levels, we believe they are independent. For an example, in this case, if you are studying the yield of 3 fertilizers, if you take observation 1, if that is coming from yield 1, and if you take observation 3, if that is coming from fertilizer 3, so those are independent. If the first observation is coming from fertilizer 1 and third observation is coming from, let's say, fertilizer 3, they are independent. So in this case, what we do is, first, when it comes to a design of experiment, we can conduct the ANOVA, one-way ANOVA. So there we can check whether the means between the factors are different or the same. Then what we can do is, if these means between factors, if they are different, or if they are the same, no problem. But if they are different, we can carry out our calculations and analysis and find out what are the differences between these factor levels, and then we can come up with better conclusions. Now, for an example, you can see here, conduct a chemical experiment keeping the temperature constant at 3 different levels: 20 Celsius, 30 Celsius, 200 Celsius, 300 Celsius, and 400 Celsius. Response is the weight of the product. Now, in this case, what they have done is they have conducted an experiment. So it's a chemical experiment. They have conducted that experiment using different temperature levels, that is 200, 300, and 400. So the response is the weight of the product. So in this case, our factors are, actually our treatment is the temperature. We are changing the temperature and checking the effect. So in this case, our factor is the temperature, and here we have 3 levels, that is 200, 300, and 400. We have 3 levels there. So in this case, we can just come up with, when it comes to design of experiments, we can compare and make conclusions with these are the equal effects and these are the different effects. Likewise, we will discuss with an example, then you will understand. But when it comes to regression, if you just compare design of experiments with regression, the difference between DOE and regression is, in regression, we talk about the association between the variables. Like if you have birth weight and age, we are talking about the variation and the association. Like when you increase age by 1 unit, what will happen to birth weight? Likewise. So in this case, when it comes to completely randomized designs, what we do is, when it comes to the most basic type of statistical design to make randomization for the treatments, we can come up with this completely randomized design. So in this case, what you have to do is, now when you have some of experimental units, when you are assigning these treatments, we have to do it in a complete randomized way. That is, now if you have, for an example, let's say you have 10 tomato plants and you have 2 fertilizers, fertilizer 1 and fertilizer 2. And we are going to assign fertilizer 1 for 5 tomato plants and fertilizer 2 for another 5 tomato plants. So in that case, when you are assigning fertilizer 1 for 5 tomato plants, you have to do it in a complete randomized way. That is, when you take any tomato plant out of these 10, they are having, that should have an equal chance to be assigned with fertilizer 1 or 2. So then only we can say it's a completely randomized design. So you need to have the equal chance to receive any one of the treatments equally. And also when you take the combinations of these experimental units assigned to the different variables, they should be equally likely. So that is how we conduct the completely randomized design. So in this case, there is, when it comes to, now if you take the example that I just raised, so that is when you have 10 tomato plants and then you have 2 fertilizers. So we are going to assign 5 fertilizer for each, 5 plants for each fertilizer. So in this case, when you take these 10 tomato plants, they should be homogeneous, because if there are differences between these plants, then when you are coming up with the conclusions, then there is a variation between plants. So you cannot come up with the conclusions and you cannot compare the effect of these fertilizers. So the most important thing is, when you are using this completely randomized design, your experimental units, they should be homogeneous. But sometimes when it comes to practical situations, it's not it's not easy to make it homogeneous, but we are trying as far as possible to take homogeneous experimental units when we conduct this complete randomized designs. So the main disadvantage is when you have differences between your experimental units. So in other words, when the experimental units are heterogeneous, then this design, the completely randomized design, it's not that effective. So when it comes to this CRD, completely randomized design, there are advantages as well as disadvantages. So if you have a look on the advantages, one is they're very flexible. So you can have any number of replicates. That is, now, as I said, if you have 10 tomato plants, and if I'm going to check the effect of fertilizer 1 and fertilizer 2, it's not must to assign 5 to fertilizer 1 and 5 plants to fertilizer 2. You can have different number of replicates. Let's say I'm going to assign 2 plants to fertilizer 1 and remaining 8 plants to fertilizer 2. So that is possible. You can have any number of replicates. There is no limit. So it's very flexible. And we can consider this with unequal replicates. So just as I said, when it comes to fertilizer 1, the number of replicates, there is no limitation, whether it's 1, 2, 3, any number. And also when it comes to the equal number of replicates, it's also not a must. That is, when you take fertilizer 1, it's not must to have 5 under that. And when you take fertilizer 2, it's not must to assign 5 plants with fertilizer 2 to be equal, to make a equal replicate. So if you want, you can assign 3 replicates to fertilizer 1 and 7 replicates to fertilizer 2. So the number of fertilizers under each factor level or under each treatment, that can be different. But when we are running this completely randomized design, when it comes to, since it is very easy for the calculations, in most of the cases, we use equal number of replicates under treatment levels, but it's not a must. If you don't like to have equal number of replicates, you can have different number of replicates. And when it comes to the analysis, when you compare with other designs, the analysis of CRD is quite simple. And when you have missing values, especially, we can reject the missing values and we can still do the calculations. So that is, the calculation is very simple. So if you look at this example, in this case, it says a group of researchers are interested in comparing 4 different methods of teaching. So we have selected approximately homogeneous set of students and then randomly allocate them to different methods of teaching. After exposing these students into these teaching methods, they have decided to measure the improvement of student IQ level. So they decide to conduct IQ test before the experiment and after the experiment, and consider the differences in marks obtained for IQ tests as a response variable. So consider the following situation. Now here, this researcher is going to do an experiment regarding 4 different teaching methods. So what they have done is they have taken students, a set of students, and then they have at the beginning of this research, they have given an exam for these students to measure their IQ level, and they have scores of all the students, and they have assigned the students with these 4 different teaching methods, and at the end of the teaching method, again they have assessed their IQ level, and then we can take the difference between the 2 IQ levels as the response variable. So if the teaching method is effective, we know IQ level should be improved. So with that, we can check whether there are differences between these 4 teaching methods or not. So we can use completely randomized design, CRD, to check whether there are differences between these 4 teaching methods. Now, in this case, let's say there are few students who have joined with the experiment. So they have faced for the IQ test at the beginning, and they have assigned for a particular teaching method. But at the end of this experiment, let's say they have not faced for the final exam. Let's say these students have been assigned with method 1 teaching. So at the end of the experiment, they have not faced for the end examination. So in that case, when we want to compare the difference between the IQ level, it's not possible because we don't have the IQ level at the end of the training of these few students. So in that case, there are missing values. No, we don't have these observations are missing in this case. So what you can do is, if these observations are missing, no problem. When it comes to a completely randomized design, you can just omit those students and you can take the remaining students. Let's say you have 7 students are remaining with method 1. So you can do the calculations with those remaining students. So even though we have a missing value, it's not a problem when it comes to completely randomized design. And then again, let's say there is another student. If you look at point 2, it says the group of researchers late found that a particular teaching procedure, let's say method 4, was not properly organized. Therefore, they found that it was not reasonable to compare that teaching method with the other methods of teaching. So in this case, when it comes to this particular example, we have 4 different teaching methods. So our factors would be, our treatments are these 4 teaching methods. So at the end of the experiment, if you find that one of the teaching method is not properly organized and it's not fair to compare that with the other teaching methods, no problem. We can omit that. We can reject that teaching method and we can just take the data set without that, and we can continue our analysis. So if you look at these 2 situations, in the first situations, some of the observations were missing because some of the students, we didn't have their IQ level. So in that case, we have missing observations. And in the second case, one of the treatments is not properly organized. So in that case, we cannot talk about that treatment. So that is, one treatment is missing. So when you conduct this completely randomized designs, you can come across with these type of situations. Sometimes observations will be missing, and sometimes the treatments, there are some problems with the treatment. So no problem. When you have these, when you come up with these situations, you can omit these missing values and you can continue your analysis, your calculations. So that is actually one of the major advantages of completely randomized designs. We can still do our calculations even when we have missing values and missing treatments in our design. But there are disadvantages of this completely randomized design as well. So as I mentioned earlier also, now when you assign these treatments, now when you take this example, if you want to check whether there is a difference between these 4 teaching methods, when you are taking these to a set of students to assign these different teaching methods, the ideal case is all the students should have the equal IQ level at the beginning. So if when it comes to practical situation, if you're really going to conduct this type of an experiment, what we do is we just, if we are going to a university, we can take a random sample of students from a same batch. So we assume that all of them are having the same IQ level, but there may be variations between students. The IQ level may be different. So they are not that homogeneous if we think about the differences among the students. So when the experimental units are not homogeneous, when there are differences between the experimental units, this completely randomized design, the completely randomized design is not that effective. So we can get very accurate conclusions only when we have homogeneous experimental units. So that is one of the problems, one of the disadvantages in completely randomized design. And also it is it is less informative than the other complex designs, because you will see when we do the calculations, when you conduct a completely randomized designs, we can just find out whether the means are different, whether there are differences between the treatments, and what are the differences between these treatment levels. Anyway, it is less informative because there are some other complex designs where you can obtain more information by carrying out an analysis. So this is less informative. That is also one of the disadvantages. And also the completely randomized design, this is actually suitable when you have less number of treatments, because when you have so many treatments, the efficiency of this is, again, there is a doubt. So this is suitable only when you have small number of treatments. So these are the disadvantages of completely randomized design. So anyway, what you have to remember is, when you want to check whether there are differences between treatments or treatment levels, you can just come up with completely randomized designs. And when you have this completely randomized design, the main thing that you have to consider is you have to take the experimental units as homogeneous as possible. And also when you're assigning the treatment, you have to do it in a completely randomized way. So that's how we conduct the completely randomized design. So the next thing we are going to talk about is, when you are coming to the analysis part of this completely randomized design, we are going to use Way Anova to do the calculations of this completely randomized design. So before talking about Way Anova, do you understand about this completely randomized design, or do you have any questions regarding that? So yesterday I uploaded all the recordings and all the lecture materials, so you can access them through Cal now. And also I have uploaded assignment 4 as well. I'm not taking marks from that, but if you want to, like, you can just do it. I have just put a submission link, so if you want, you can submit that, because then when you have a target, it's easy to complete the assignment. That's why I put it. So you can just do it. Anyway, we'll be discussing about assignment 4 on Friday. Okay, so if you have no problems, we can continue with Way Anova. So when it comes to Way Anova, in Way Anova, we consider only one factor. That's why we call Way Anova. Now, when it comes to completely randomized design, you have several treatments. Now, in the example that we discussed, we have 4 teaching methods. So let's say you have 2 fertilizers to assign. So you have different treatments. But when it comes to Way Anova, we can talk about only one factor. So what we do is, when you have different treatments in complete randomized design, and when we use Way Anova to analyze that, we can use the treatments as the levels of these factor. Since you have one factor, we can take the levels of these factor as our treatment. So that's how we use Way Anova to analyze this complete randomized design. So actually, when it comes to this complete randomized design, there are two models that we can come up with. So one model is known as the treatment means model. So in treatment means model, what we do is, there we, let's say you have T number of treatments. You have, for an example, in the previous study that we discussed, you have 4 teaching methods. So that is, you have 4 treatments. So in that case, the number of treatments you have usually denoted by simple T. So in that particular example, T is equal to 4. So the level of the, now since when it comes to ANOVA, we take the treatments as levels of the factor. So here we denoted by the levels of the factor by simple T, that is the number of treatments you have in your study. And then, so what you can do is, so any observation of this level, you can denote it by I. So that is, I can go from 1 to T, since you have simple T number of treatments, right? And if you take any treatment, observation of any treatment as I, since you have T number of treatments, I can go from 1 to T. And then when you take, let's say, when you take the first treatment, let's say you have assigned 10 units, 10 experimental units. When you take the second treatment, let's say you have assigned 7 experimental units. So under each treatment, we have to assign experimental units. So when you take I treatment, the number of observations you have is denoted by Ni. So in that case, if you take the T treatment, that is, you have simple NT number of observations. So if you want to if you take sorry, this is the total number of observations. So when you take the ith treatment, you have Ni number of observations. So if you take the total of all the observations, that is, if you take total of, since you have T number of treatments, that is, I goes from 1 to T. So if you take the total of all these Ni values, that is equal to that is equal to NT, which is equal to the total number of observations. That is, for an example, if you take, let's say, in the fertilize example, you have, in the teaching method example, if you take teaching method 1, you have teaching method 1, and you have teaching method 2, teaching method 2, and then we have teaching method 3, and then we have teaching method 4. So in the previous example, these are the 4 treatments. So here we take the teaching method as our factor when it comes to ANOVA, and under that factor you have these 4 levels. So let's say when you assign students, let's say for the first teaching method you have assigned 10, and for the second teaching method you can assign 10 for each, or else you can have different number of replicates. Let's say here 8, and let's say to this one you have assigned again 10, and here let's say you have assigned 7. So now in this case, here you have 4 number of treatments. So you can take, this is treatment 1. So in this case, simple T is equal to 1. Here, this is simple T is equal to 2. Likewise, here you can see T can goes from 1 to 4. In this case, simple t is equal to 3, and this is the last treatment. So this is simple t is equal to 4. And when you take the first treatment, you have 10 observations. So number of observations you have in the first treatment, that is denoted by simple n1, that is equal to 10 here. In this case, you have 8 observations. So that is denoted by simple n2. In that case, that is equal to 8. In this one, we have again assigned 10 units. So that is number of observations you have under this treatment is denoted by simple n3. That is again you have 10 units, and then here we have assigned 7 units to this method. So simple n4, that is equal to 7 units. And in this case, when you take the total number of observations, 10 plus 8 plus 10 plus 7, so you have to, that is, we are adding simple, if you want to take the total of observations, that is simple n1, simple n1 here. So simple n1 plus n2 plus n3 plus n4. This will give you the total number of observations, which is equal to 10 plus 8 plus 10 plus 7. In our case, it's 35. So this is denoted by simple NT. So the total number of observations in your completely randomized design is denoted by NT. So T is the number of treatments you have. Under one treatment, you can talk about the number of observations you have. So if it is the ith treatment, you have simple NI number of observations. So you have to take the total of all the NIs to find out the total number of cases that you have taken for your study. And then if we, let's say we have one particular student whom we have assigned the second teaching method, and that one is the third student whom we have assigned the second teaching method. So in that case, that is the student. If you take that student as Y, we have assigned the second teaching method, and that student is the third students whom we have assigned the second teaching method. So that is denoted as Y23. So that is the jth observation under ith treatment is denoted by Yij. So first you have to denote the observation by its treatment number. Then you have to talk about the observation, right? So this is the second student, this is the third student who have been assigned with the second teaching method. So likewise, we use this we use this index J to identify the position of the observation. So in that case, when you take Yij, that is the jth observation for the ith factor level. So here, when it comes to the ANOVA model, now in this case, when it comes to this treatment means model, what we do is we have our observation Yij, and that is equal to mean of the treatment, which is denoted by mu I plus the error. So Yij is the response of the jth trial of ith factor level, and mu I is the mean of the population of observations under treatment I, and this random error is the error term of the ijth observation. So here, if you're going to write down the treatment mean model under completely randomized design using one-way ANOVA, this is how you have to write. So you have the observation, and observation is expressed using the mean value of the treatment plus the error term. So in this case, we have just as in simple linear regression and multiple linear regression, we have assumptions here. So one assumption is these error terms are normally distributed with zero mean and constant variance. So And also the other thing is these errors are independent with each other. So when you take the error of, let's say, the second observation of the first treatment, and if you take the error term of the third observation of the first treatment, again, the error terms are independent and they are normally distributed with a constant variance. So these assumptions are valid under completely randomized design as well. So here, there are some important features now when you look at this model. So when you take this model, based on this model, we can come up with some important features. Yeah. So if you look at this model, you can see in this case, the observation that is coming from the ith treatment and jth trial. So that is actually a summation of two components. You have a random error and you have a mean. But in this case, when you look at the mean, here they are talking about the mean of the ith treatment. So when it comes to a particular treatment, whatever the observation, whether it's the first observation, second observation, no matter what is the observation level, the treatment they have considered, the mean they have considered here for the full treatment level. So here the mean value is a constant. So you can take the mean as a constant. So we can see here the observed value of y, that is actually a combination of this constant mean and a random error. So in this case, if you take the expected value of this one, so if you take the expected value of your left hand side, that is the expected value of yij, then you have to take the expected value of your right hand side. So in that case, when you take the expected value of this, right? So again, we can, in your right hand side, when you have to take the expected value of mu I plus the random error, then we can rewrite it as expected value of mu I plus expected value of Eij. So we know expected value of Eij, it's having a zero mean, that's equal to 0. So expected value of yij, that will be equal to expected value of mu I. So mu I is a constant. So in that case, we can write expected value of ei is equal to mu I. So that is for all the observations under ith treatment have the same expectation, that is equal to mu I. We can prove this. So we'll talk about the proof later. And likewise, if you just take the variance, so if you take the variance of yij, so if you take the variance of this, if you take the variance of your left hand side, you have to take the variance of your right hand side as well. Now in this case, when you take the variance of yij, since they are independent, you can rewrite this as variance of mu I plus variance of the error term. So mu I is a constant, so the variance will become 0. Then you have the variance of the error term. So variance of the error term is sigma squared. So you will have the variance of yij is equal to sigma squared. That is again a constant. And then the error terms are normally distributed. We ask for the assumption. So if the error terms are normally distributed, yij is a linear combination of this error term. So we can say these observations yij is also normally distributed. And then the error terms are assumed to be independent. So that is when you take the outcome of any trial that has no effect with the outcome of the other trials. They are independent, right? Even under the same treatment, you have no connection in between. So these are some of the main features under completely randomized design. And now let's see how it looks like when you have when you have to assign these treatments, when you have observations. Let's see how your design looks like. So it looks like this. Now you have simple T number of treatments. So that is starting from 1, 2, 3 up to simple T number of treatments you have here. And then under treatments, you have several number of replicates. That is, for the treatment 1, we are going to assign 10 observations. Treatment 2, again, it can be 10 or it can be some other number. So anyway, under each treatment, you have different number of replicates. So here we have taken, let's assume that we are going to assign the same number of observations to all the treatments. So that is, when you take treatment 1, here you have assigned 1, 2, 3, 4 up to R number of observations, experimental units. So that is, if you take the observed value of this first one, that is coming from first treatment and first observation. So you can denote it as Y11. If you look at the ith treatment, and here if you look at this jth observation, so for this particular experimental unit, we have given the ith treatment, and that's the jth value. So you can denote it as Yij. So what happens here is, now when you look at, now here by rows, they have given you the treatments. So when you look at the first row, you have, if you take the total of all the observations in the first row, that is, you are taking the total of all the values which belongs to treatment 1. So since we use Yij to denote the observation, now when you take the total by rows, you're not changing the treatment. Treatment is there, right? So that is, we are taking the total of the first observations of the first treatment, and when you take the total of the second row, that is, we are taking the total of the observations of the second treatment. So the total we can denote by Yi dot. That is Y1 dot, Y2 dot, Y3 dot, likewise the total. And then the mean, we can talk about the treatment mean, because here we know under each treatment how many observations we have. We have R number of observations here. So this total we can divide by R, and then we can talk about the mean of this treatment, that is Yi dot bar. So in this case, if you take the third treatment, that is Y3 dot, if you take the row total, and if you divide that by R, you will have Y3 dot bar. Right? And here, if we want to talk about, if you take the summation of all the observations, that is, if you first, you can take the total of the treatments, where then for that you can take, you can just write it, the observation is denoted by Yij. So if you are taking the treatment total, J can goes from 1 to Ni. Then again, you can talk about all the, when you take all these totals, you will get that overall total. That is, since we have T number of treatments, I goes from 1 to T. So this overall total, that is denoted by Y double dot. And if you have this overall total, if you divide this overall total by total number of observations, which is denoted by NT, then you will get the overall mean. So the overall mean is denoted by Y double dot bar. So we know when it comes to our ANOVA or regression, we are using the least square estimations. And when you are using the least square estimation, the basic idea is you have to take the errors and you have to take the squared summation of the errors, and we have to minimize the squared summation of these errors as much as possible. And then we have to find out the respective parameters. Now, in this case, since our model is Yij equal mu I plus the error term. So if you just write an equation for the error term, you will have Yij minus mu I. So here, this error, you can take the squared summation of all these errors. And when you minimize that one, you can find the least square estimates for the ANOVA, right? And in this case, if you take these errors, you can see Yij minus mu I. And if you want to find out an estimate value for these errors, you can take mu Ij minus mu I hat. So the mu I hat is that mu I means the treatment mean. So as for the least square estimates, we can show the estimator for the treatment mean is equal to the sample treatment mean, that is Yi dot bar. So you can rewrite the residuals as Yij minus Yi dot bar. So we'll discuss how to do these calculations manually. Now, this is the basic idea between the treatment means model. So do you have any questions regarding the treatment means model? Okay, so if you have no problems, now when it comes to this completely randomized design, we can go with this treatment means model, or else now when you look at this treatment means model, the model that we just discussed here, we are talking about the overall treatment mean. Now here, if you really want, we can come up with the treatment effects model, where you can talk about the effect of the eye treatment. So in that case, what we are going to do is we are going to replace this mean value of the eye treatment by overall mean and the effect of the eye treatment. So in that case, we can rewrite this model as Yij is equal the overall mean, that is mu dot, plus alpha I, that is the effect of the eye treatment, plus the error term. So we know I is the treatment level. It can goes from I can go from 1 to T, and J is the index that we use to denote the observation. It can goes from 1 to Ni. So when you are using the treatment effects model, the assumptions are again the same, because in the treatment effects model also the errors are normally distributed with zero mean and constant variance, and then the errors are independent. But here you can see we have now two new parameters, that is mu dot and alpha I. So in that case, when it comes to the overall mean you can use this formula to calculate the overall mean. That is what we do is, if you have the mean for the eye treatment, since you have Ni number of replicates under eye treatment, so we multiply mu I by Ni, and then we divide it by the total number of observations, Nt. And here, when it comes to the treatment effect, what we do is we take mu I, that is the eye, the mean value of the eye treatment, and we subtract the grand or the overall mean from that, and that would estimate alpha I, the effect of treatment I. You can see if you just substitute mu I minus mu dot to alpha I here, to this treatment effects model, then you can see again this will convert into treatment means model, right? So it's the same thing, but here we have rearranged the terms in a different way to analyze the effect of the treatment separately. So whatever the model that we are going to use, we can do the calculations and we can come up with the same conclusions. So in this case, these are the two models that we are going to use. when it comes to completely randomized design. So I'm going to give you a small homework. That is, if you look at this data set, it says an engineer is interested in determining whether percentage in fiber affects the tensile strength. Then the engineer run the experiment with 5 levels of cotton percentages and 5 replicates for each level, and test the hypothesis that cotton weight percentage affect the tensile strength of the fiber. So here, what we want to do is there are different levels of cotton percentages, and here you can see 5 different levels of cotton percentages are here. And when this cotton percentage is changing, the strength of this fiber is also changing. So they have just gathered information regarding the strength level under these 5 different cotton percentage levels. So now we have to check whether actually this strength is different between these different levels of cotton percentages. So you can see there are 5 levels of treatments and 5 levels of replicates under each treatment. So what I want you all to do is you have to take this data set and I want you all to do this calculation. Right? You have to identify what is your treatment and what are the replicates, and you have to find the row total and mean total and also the grand total. So then it will be easy for us to do the calculations. Right? So when you are coming for the Tuesday session, you have to do that calculation and come. Do you have any questions up to that point? You understand what we discussed today? තේරෙනවද ළමයි අපි discuss කරපුවා? Do you all understand? Let me ask from one of you. I don't know whether you all are sleeping. So let me ask. Himaya, do you understand what we discussed today, Himaya?
Yes, ma'am.
Okay, right. So good to hear at least one of your voices. Yeah, I will upload this lecture note and the recording as well. Okay, then I'm going to stop from this point. So on Friday, we'll discuss the assignment. And on Tuesday, we'll discuss how to do the calculations with Way Anova in completely randomized design. So you have to do your homework and come. Do just prepare this completely randomized design table for this given example and come on Friday. Okay, then I'm going to stop at this point. Thank you and have a nice